This video is going to show you how to draw ray diagrams to find images formed by spherical mirrors. In particular, I'm going to do concave mirrors this time, which is where the silver is on the inside of the spherical part. So the first thing you need to do is you need to draw the part of sphere that represents your mirror, like this, and then draw a line that goes through the center like that. We call that the principal axis. Label the center of curvature for the mirror and the focal point for the mirror, and then draw your object, which is usually represented by an arrow. All right, now it's important if you are trying to get some kind of quantitative answer out of this, it's important that you're very careful with your measurements, that you get the radius of curvature of the sphere correct, and that you put C in the right place and F in the right place and your object in the right place. You have to measure with a ruler and use a straight edge for your principal axis, all of those things, because if you don't get the measurements exactly right, then your quantitative answer will not be okay. Usually ray diagrams and mirror images are used to help you learn how the image is formed and where, not to get a quantitative answer. We use the mirror equation for that. Once you've got everything drawn and labeled, you draw the three principal lines. First, it doesn't matter which order you do it in, but the first one that I like to draw is the one that comes over the top of the object parallel to the principal axis and then reflects through the focal point. So it comes in over the object parallel to the principal axis and then reflects through the focal point. Okay, the second one is one that passes over the top of the object through the center of curvature, and that reflects back on itself. Okay? Then the third one passes over the top of the object through the focal point and reflects parallel to the principal axis. There we go. And then the image is where the three lines intersect, or appear to intersect. Here they really do intersect, and because they really do intersect, that is what we call a real image. I'll mark the image in bold so you can distinguish it from the object. So you can see that the image is going to be a real image because the rays really do intersect there. The image is going to be upside down or inverted compared to the original object, and it's going to be smaller than the original object. Right, that is how you draw the rays for a concave mirror to find the image if the image is real. You get a real image when the object is further away from the mirror than the focal length. Now let's do one where the original object is inside the focal length and see what happens. We still approach it the same way. You still draw your mirror and your principal axis, mark your focal point and the center of curvature, and then you draw the same three principal rays. We'll draw one that comes in parallel to the principal axis and reflects through the focal point. Okay, then we draw one that goes through the center of curvature and reflects back on itself. It reflects through the center of curvature, passes over the top of the object, and then reflects back on itself. So we can just draw a little arrow going the other way too, because that's what it does. And then finally, we draw a ray that goes from the focal length over the top of the object and then reflects parallel to the principal axis. It goes through the focal point and over the top of the object, reflecting back parallel to the principal axis. All right, well, we're done drawing the principal rays, except, those don't converge anywhere. The last one we drew is going off to the left, straight to the left. And then the one through the center of curvature is going down and to the left, but the first one we drew that came through the focal point is also going down and to the left, but at a different angle. So those three rays are never going to intersect with each other. If I was a person looking over here, so let me draw the person's eye. We draw the observer's eye over here. So here is the observer who is looking at these three rays, and they will see those three rays coming and they think, well, those three rays don't converge anywhere. But to this person's eye, they look like they came from the same place. The brain thinks that rays travel in straight lines. When they're processing optical signals, they don't consider mirrors. So what we have to do is trace those lines backwards and see if they appear to come from the same place as each other, and in fact, they do. I will do that with my pen instead of with the software. That one looks like it came from here. That one's going to look like it came from straight back. This one is going to look like it came from that direction. And the one through the center of curvature is going to look like it came from that direction. So, they do appear to converge right there. There is going to be an image that forms behind the mirror. There, since the rays don't actually converge, they only appear to converge, we call that a virtual image. And you can see that in this case, the image is bigger than the original object, so it's magnified, and it's upright. So this is the kind of mirror that you might use for a shaving mirror or a makeup mirror, because you stay right side up. You know, your face doesn't appear to turn upside down in the mirror, which wouldn't be very helpful if you were shaving or putting on makeup. It magnifies it, and it doesn't really matter that it's a virtual image. You can still see it, so it will help you do something like that. If you're doing these ray diagrams, it's quite often that you may do one, if you're not really careful with your distances and straight edges and things being parallel and so forth, it's quite often that you will get something that's sort of like this. I've got one more example here that you can see that I drew the three principal rays. Here's one that goes in parallel and reflects through the focal point. Then here's one that goes through the center of curvature and reflects back on itself. And then finally I have one that goes through the focal point and reflects parallel. And those three rays don't intersect. They sort of do. They might intersect. You know, you could say, well, they sort of intersect right in here, because two of them intersect here, two of them intersect here, and the red and the blue one, you know, those two are going to intersect down here somewhere. So you would think that, okay, probably we're going to have an image that's upside down and real there somewhere, but because I wasn't really careful with my distances and parallel, and see, like over here, you see, if you look at the graph paper really closely, you see how it's on the line over here, but it's not on the line over here. So I wasn't really careful. Sometimes the rays will not all converge at exactly the same point. All you'll be able to tell is the rough area where they are going to converge, but that's okay. We can still determine from this that we're going to have an upside down real image, even if we don't know exactly where that image is going to be. And that's it. Now you can draw ray diagrams for concave mirrors.